Hi, it's
One
Mr.
more
Anderson, and
here.
welcome to Biology
Hold
Essentials
on,
Video
everybody.
31.
You've
This is
got
on
to know
gene
right now.
regulation. In
This
other
no
words, how
matter
we
what.
express a gene or not.
What did
How
you
we
mean?
make a
I
protein
can't
or
believe.
not.
I
And I
can't
want to
believe.
start with
You
an
can't
organism that
believe
lives
it
in
right there.
our
I'll be right back. I'll be right back
intestine
before
called E.
lunch.
coli.
You
E.
know, just in
coli is
case.
interesting
All
in
right.
that it eats whatever we
There's
eat.
a very
And so if I
good.
eat bacon for
Very good
breakfast,
with
it has to
outer.
break
You
down
know
the
what's
proteins and the
happening? You're
lipids in the
not
bacon.
asking. This is
If I have
trust
cereal,
me.
it has to break down the
Trust me, okay?
carbohydrates.
Wait a
If I
minute
have
here.
milk, it
There's
has to break
Angry
down the lactose.
Alicebat.
And so what's interesting about an E. coli
Not
is that it can go
all
from
your
an organism
place.
that has
The
0
grass at
proteins to break down
Nora.
lactose
We don't
to
have
one where
Nora
50% of the weight of E. coli is simply
dedicated enough.
enzymes that deal with
It
lactose.
is a
And it can do
lie.
it like that.
I've
And so
been
how do they do
relying.
that? They
You
do that through
can't do
gene
it.
regulation.
What
And
is
so
the
in this
real here?
podcast, I'm going to talk about gene
Here, the
regulation.
enterprise
Before I
is
do
like
that,
this
I want to
all
get some
over for
terminology that I'm going to
entertainment.
use a lot out of the way.
There is a
And so a
distribution.
regulatory
What
gene is going to
kind
be
of
a gene on the
distribution is right
DNA that
there?
regulates
Not really. This
another
is an
gene somewhere
emergency.
farther
You're
down. A
dangerous.
regulatory
You're
sequence will usually be
dangerous.
found just
I
above
can't
the
believe
gene.
it right
And so
there.
what do I mean by that?
Besides,
So if
what
DNA
don't
looks
you
like
do right
this,
there from the outside in?
the gene generally will be
What
down
are you
here
doing?
that we want to
I
express
can't
or
believe
not.
it. You must
A regulatory
awesome.
gene will be somewhere
That's
else in the
me.
DNA.
It's just
It
a game
secretes
like
something
this.
called a
The weird
regulatory
stuff.
protein, which then can grab onto a
You're a
regulatory
dog.
sequence.
That's a
An
dynamic.
example of a regulatory sequence I'll talk about is called a promoter. Once this is all fit up, then we can have an RNA polymerase actually make the gene. And so I'll go through that terminology, but when I'm talking about regulatory gene, regulatory sequence, those both deal with DNA. But when I'm talking about a regulatory protein, that's coming from somewhere else to help express the gene or not. As far as gene regulation examples, most of what we know now comes from bacteria. And so I'll talk about positive and negative control. Positive control example I give you is the lactic operon that deals with lactose, and the negative control is the trip operon that deals with tryptophan. And then finally, I'll show you what we know about eukaryotic gene regulation and how they use transcription factors as activators, repressors to either express a gene or not. And so this is how genes are made or expressed. Remember, we start with DNA, and that DNA eventually makes messenger RNA, which eventually makes proteins, and those eventually make you. And so any step along the way, we can actually regulate the gene. So we can regulate it post-translationally, post-transcriptionally, so we can do it everywhere. But in general, most of the regulation I'm talking about is just going to be from DNA to messenger RNA. Do we express the gene? And so this is generally what goes on. We've got a gene like this. Upstream of that, we have a regulatory sequence. An example of this in eukaryotes would be the tata box. And the reason it's called the tata box is you have a thymine, adenine, thymine, adenine. And on the other side, you have tata backwards, complementary to that. And so this is simply a sequence above the gene that allows the RNA polymerase to get on. And so we have a regulatory protein coming from somewhere else, remember, another regulatory gene, maybe downstream or upstream from this whole gene. The regulatory protein, an example, could be the tata binding protein. This is found in us. It'll grab onto the tata box. Let me get rid of the writing. And it allows RNA polymerase to grab on and actually express that gene. And so if we didn't have the sequence, if we didn't have the regulatory protein, we couldn't make the RNA polymerase, and we couldn't make the protein. And so that's basically how genes are regulated or not. And so let's talk about how this works in the
What's going on out there? Angry Alicebat!
So the way that they tweak what I just said is the unique thing about bacteria is instead of just having one gene, they'll have a number of genes. And so they'll have 3 genes. All the genes required to deal with lactose will be put right next to each other. And so we've named those the LAC-Z, Y, and A gene, but they each make a protein and they each help break down lactose. Above that, they'll have a regulatory sequence called a promoter. Remember, that's going to be where RNA polymerase grabs on. And the other thing they'll have in an operon is called an operator. An operator sits right between the promoter and the gene. And the way I like to think about it is it's like an on-off switch. And so it can either be set in an on position or it can be set in an off position. And so it regulates whether or not we turn the genes on or we don't. The other thing that I'm going to add here is something called a repressor. A repressor will plug right into the operator. So it's going to fit right here. And as long as the repressor is available, RNA polymerase can't get on. And so this would be when the pressor is here, the operator is now in off position. In other words, we can't make these genes. This repressor I'm going to show you is showing what's called positive control. And what do we mean by positive control? What I said was when lactose shows up, we want to make all the proteins to break down and deal with lactose. And right now, there's no lactose present, and so it's off. But let's say lactose shows up. In other words, I drink a glass of milk. Now there's lactose. So the lactose shows up. The lactose, you'll notice, is going to fit perfectly into that repressor. And when it fits in the repressor, it changes the conformation or the shape of that protein. In other words, now the repressor doesn't fit in the operator anymore. In other words, it lacks these little prongs, we'll say, that fit in the operator. Okay, so lactose is present, repressor is now off. Well, who can grab on? RNA polymerase now fits. RNA polymerase can fit. There's no repressor. RNA polymerase is going to run down. It's going to make each of the messenger RNAs for each of those lac genes. Each of those are going to make a protein. And each of those are going to break down the lactose. And so we can deal with the lactose and we can metabolize that lactose. So now the lactose is gone, what's happening to our repressor? It's going back to that original shape. And so it's a cool way we can have positive control. If lactose shows up, then we make all the proteins that can actually deal with that lactose. Shows up again, we're going to get rid of that repressor. And so that would be positive control. That's an example of negative control. Stop! Well, negative control we learned about from the trip operon. Trip operon, instead of having those three.
What's wrong with you? Don't ask me an answer. What's wrong? Will you do it? No, you don't. No,
the way it works is it's actually off when tryptophan or whenever that chemical is present. And so tryptophan, remember, is an amino acid. We need it to make proteins. And so bacteria, as long as tryptophan is present, they don't want to have to make tryptophan on their own. And so the way it works here is that the actual tryptophan fits in the repressor. It gives it a shape that actually blocks the RNA polymerase or the making of those proteins. But let's say, for example, that your diet doesn't have tryptophan.
Come on, everybody,
join in! What does the bacteria do? Well, now the repressor is going to change shape. It's going to change shape. That allows RNA polymerase on. RNA polymerase is going to quickly make those 5 proteins, and then those 5 proteins are going to make more tryptophan. So the tryptophan fits again, and it's going to turn off. And so what that gives us is really cool control as far as the bacteria goes on if we have positive control in the case of lactose whenever it shows up, and we want to break it down, or tryptophan control, negative control, when it's there, then we want to turn it off. So simple, neat engineering solution to a real-world problem. Now, we don't have operons. Remember, in between each of our genes, we'll have long stretches where there's actually junk, quote-unquote, DNA. And so the way it works in us is a little bit different. We use what are called transcription factors. So RNA polymerase is here, but RNA polymerase can't get on until we have a number of transcription factors. And so let's say we want to make a protein as well in eukaryotes. To do that, we have regulatory factors. Those are actually made by regulatory genes. They could be somewhere else in the DNA, or they could even be outside the nucleus in the cytoplasm. So in order for us to transcribe a gene, it takes a little bit more, it's a little more in depth. First of all, the transcription factors will allow the attachment of RNA polymerase. We'll have other transcription factors that will actually hold it in place, but you can see that we're not actually making the gene. And so in order to make the gene, the DNA upstream of that will actually have to fold. It'll get more transcription factors, and you'll notice that still nothing's going on. We still don't have transcription.
No, you want me alone.
Until that actually folds back and activates that RNA polymerase to go now and make that protein, or make the RNA and then eventually make the protein. And so how does it work in us? We don't really have these on-off switches. I don't know if you can see my hand. But what happens is the DNA actually folds back on itself, and it can activate genes in other places along the genome.
There's an
And so
emergency
it's
alert
a
system.
different form of control. It's more complex
Honey,
form of control,
no,
but it
that.
really requires
No,
input from
that.
all these other
I have.
transcription factors.
No,
So
it's
that's
power.
gene regulation, and I hope that's helpful.